All right, this is our settlement of piles lecture. This is lecture 18. Our learning objectives will be to determine the settlement of a single pile and determine the settlement of a pile group. So first we're going to talk about how the load is transferred from the column to the pile. When we load a pile to its working load, what happens? Well, what happens is as we load the pile head starts to move down and different parts of the pile capacity is transferred. So first we talked about skin friction. As the pile moves down, skin friction is mobilized. So most of the initial capacity is carried through skin friction. And then as the pile continues to move down, the bearing capacity base portion starts to carry some of the load. And you can see in this graph here that this is a 6-inch by 4-inch pile. Here's a load capacity as we load it. And as we load the pile down, it starts to carry more and more capacity. You can see it here as we load it. And this is also showing with time that as the setup is occurring, that there is additional capacity over time from this clay starting to set up. So how much movement does it take to mobilize the shaft resistance or the skin friction? And how much movement does it take to mobilize the point resistance or end bearing? So when we look at our pile sediment, we can say that when the surface loads on the pile stresses the soil will consolidate and compress, and the pile will also settle. The load transfer between the pile and the soil represents a relatively complex phenomenon. So it's affected by the stress-strain time, and it's also affected by the failure characteristics of all the elements in the system. Because of our inability to deal with these complexities, most methods are relatively simplistic. And why does the settlement occur? Well, it occurs because, and what does it consist of? So these are some of the questions we're going to look at. And we must remember that soils are not linear. They do not exhibit a linear relationship when they stress strain. So once again, it's very complex, but we're going to simplify it. In sands, it's generally elastic. We assume the settlement to be equal to 1% of the pile head diameter plus the elastic compression, which we're about to calculate, of the pile. And in clays, it's more complicated because not only is the pile itself compressing, but the soil around it is starting to consolidate, and then over time, there's creep. So a lot of the analysis and prediction methods we've had come from engineering design practices, and they're typically empirical in nature. Often, the settlement calculation of pile group is often not performed. However, this practice is very unsatisfactory and it can cause a lot of problems. So the total settlement of a pile consists of 3 components. The first component, so P total is the total sediment. The next is the axial deformation. So this is how much of the pile is deforming in the axial portion of the pile. Then we have the settlement of the pile tip due to the load at the pile at the top. And then we have the settlement of the pile tip due to the load along the shaft. And both the tip and the shaft pile include elastic and consolidation and creep components. The pile itself is going to deform based on its material properties. So the pile is elastic compression of the pile, and it consists of the where the QP is the point capacity and QS is the shaft pile load. L is the length of the pile, E is the modulus of elasticity, and we're given a typical modulus of elasticity for steel and concrete. And then A is the area of the cross section of the pile. So if it's circular, you calculate that, or if it's rectangular or square. So the load settlement curves show for small to medium diameters are under working loads are typically less than 3/8 of an inch, and that includes a factor of safety greater than 2.5. For diameters above 2 feet, the settlement problem is increasingly difficult. It requires separating the valuation of the skin friction and the base load effects. In the 1959, Meyerhoff suggested the settlement of a single pile under load is best determined by a representative load test on the particular site. And we'll talk more about load tests in our next lecture. So based on a lot of studies, Meyerhoff suggested this equation. It's for driven piles in sand, not underlain by a softer layer. And you can see here the settlement is calculated by the base pressure times the diameter and divided by 30 times the ultimate bearing capacity, or B divided by 30F, where factor of safety of greater than 3 on ultimate load. So there are more sophisticated analysis available. So you can use different load transfer methods using relationships to the pile resistance and the pile movement. There's also the theory of elasticity methods, numerical methods such as FE, and boundary element methods. But they're not really caught on because why? They're more expensive and time consuming. Here's the graph we talked about or the image we talked about last time, where when you have a single pile, you have a small stress zone. When you have a larger pile group, you have a larger stress zone. Now, when we're talking about the settlement of pile groups, we want to know that this is still a very daunting task. There haven't been a lot of testing on this. Typically, they only use simple methods due to the complexity of the issues. And one researcher, Polos, has characterized some methods available to estimate settlement, and we'll have a handout table. So Skimpton also suggested that using this equation, which is based on empirical testing, and you can see here it just basically takes into consideration the width of the pile in feet and the diameter. Meyerhoff also suggested one for sand for a square group. So here you can see the equation for that. There's also been some correlations with SPT data. So if you have SPT and sand, here's another equation for calculating settlement based on the width of the pile group. Here's one based on CPT. So CPT data can be used to also estimate the settlement in cohesionless soils. For pile groups, you can use the 2-to-1 method, which is what we talked about last time, and I'll work an example in class where you basically distribute the stress zone to at a lower depth. And this was developed by Terzaghi and Peck, and you spread, it's called the load spread method, where the load is assumed to be carried by a theoretical fitting at 1/3 the pile length from the point of the pile. You can also use a consolidation equations, and it's used for some sand soils using elastic methods. So in summary, pile settlement is very complex. A lot of simplified methods are currently used in the profession, and typically profession relies on high factors of safety against ultimate load to carry the working load with manageable deformations. In class, I'll work a couple examples and also give you more handouts.